Okay, so welcome to part 2 of the video notes on finding limits analytically. We started by looking at properties of limits, and now we're going to actually do some examples of finding limits analytically. The first example, we're going to actually find the long way using the properties, just so you can see the value of the properties. So get this pen going. Just know that after this first example, it's not necessary to find the limits analytically this long way, but the properties are what allow us to take the shortcuts, and I do want to at least show that in one example. So let's find the limit. Goodness. Okay, maybe not. I don't know why it keeps going back. Of 4x squared plus 3 as x approaches 2. Okay, right down here in the space. Okay, below here. Okay, what we do normally is we would just evaluate the function at 2. That is, plug 2 in. And when you do the calculations, you're going to get 4 times 4, or 16 plus 3, you're going to get 19. And that's all well and good, and we know that's the answer. And after this example, that's exactly how we're going to find the limit answer. But right now, let's just go ahead and see the value in using or knowing the properties, okay, what they allow us to do. Okay, looking at the properties that you have before you, okay, one of the properties says that the limit of a sum is the sum of the limits. So that's the first property I'm going to use. Now again, remember, this is not the way we're going to actually find limits in the future. I don't know what's going on, and if you can see that there, yikes. I hesitate to say that we're applying the distributive property here with this limit notation, but that property allows us to do this and break it apart. Okay. That's the sum property. Okay. Now, working on this term right here, what you might notice is that we have a scalar, and that scalar, that real number, that factor is 4. And so the first property up there says that, okay, we can multiply 4 the scalar times the limit of x squared. Again, remember, we're not doing this the long way every time. Just wanted to illustrate the usefulness of the properties. Okay, and if you look way back up at the top, this is actually one of your basic limits, and it's the first basic limit that we saw. This is a constant, so as x approaches 2, then of course that's going to be 3. And you can put 3 down here now and just know that you're going to have to carry it down through the problem. Okay? All right, if you might notice here that we have a power going on, so we're going to use the power property that we saw too. So that would look like this. And then the square would go on the outside, and then I'm just going to bring down the plus 3. Okay? And then running out of room here, let's think of this as just evaluating our limit at this point that we plug 2 in for x. So the value of this bracket would be 2. And so we have 4 times 2, which is in brackets, squared, plus 3. And of course, that's equal to 19. And we saw that the shortcut way. And in all future limits, when we solve them analytically, we'll certainly want to do that as well. Okay? Okay, what I've done is I've turned the paper over. So we're going to do the examples, the additional examples on the back of this paper as well. All right, so we're on example 2. Again, we're not going to use the properties, but if we look at this example right here, the very first thing you want to try when you're evaluating a limit is try the direct substitution method. And really, when you're dealing with a rational function here, your only concern truly is going to be the denominator. You want to avoid dividing by 0. So just real quick on a quick inspection, evaluate the denominator at x equals 1 and you get 2. There shouldn't be a problem with this. So let's go ahead and substitute 1 in everywhere we see x. And when that's all said and done, it looks like we're going to get 4 over 2, and that's just 2. So always try direct sub in. All right. Let's look at another example here where we may have a little bit of trouble and have to figure out what else to do. So the limit as x approaches 9. The square root of x minus 3 over x minus 9. Okay, yeah, and what we see here is that when you evaluate this function at 9, you're going to get the square root of 9, or 3 minus 3, which is 0. And that's not, a problem to have 0 in the numerator, but the problem is you're going to be dividing by 0 as well. And we call that indeterminate. When you do a quick inspection, you see 0 over 0, indeterminate. And what we've been doing is we've been factoring. Well, we could factor. There are two ways that you could actually solve this problem. I'm sure there's more, but we're going to look at two. You could factor. You definitely could do that. It's not very comfortable for students, but let's take a look at that. You're probably wondering, what is she talking about? How are you going to factor this? Okay, well, look at the denominator. We know 9 is a perfect square. Well, I can factor x into square root of x times square root of x. So, and you can see the advantage in doing this is that now you have a common factor and you're able to cancel that common factor. And if you think about the graph for just a minute, what we've talked about, that what's happening on the graph at x equals 9, well, when you have that common factor and you cancel it, we look for the 0 of the canceled common factor, and we see that when x is 9, that in this binomial we get 0, and this one we get 0 too, and that's resulting in us having a discontinuity on the graph. All right, now let's see what's left. If I'm going to clean this up, which I'm going to try and do so down here. Yeah, I don't know if there's much cleaning this stuff up. Okay, let's look at the remaining problem here. What we're going to have is 1 in the numerator. We divided this out. Okay, over square root of x plus 3. Okay, so now when we evaluate the limit, I can call this 3b and I can call this 3a because as mentioned earlier, we're going to use two different techniques in solving this problem. Okay, so the factoring works nicely there. Let's look at the other strategy. If you don't quickly see that you can factor the denominator into a sum and difference of like terms, what you might want to notice first of all is, go ahead and try direct substitution. You get 0 over 0. At this point right here, you could use the strategy of multiplying by the conjugate. Oops. Okay, go away. And you may have forgotten what conjugate is, but the conjugate, when we find the part of this problem that has the square root in it, okay, we can build square root of x plus 3. And what we're doing, in fact, is changing the operation sign to its opposite. So if it's subtraction here, we change it to addition. If it's addition here, we change it to subtraction. And that's the only change we make. What you can see here is that we have a sum and difference of like terms. And And that's what you're getting when you get a conjugate, because the purpose is usually to multiply them together. Okay, so we're building the conjugate on top. So we're going to retain the value of this expression right here, a function. So, and to do that, we would want to build a fraction that is an equivalent form of 1 by using the conjugate that we used up here and then replacing it down here. Okay, now let's see what happens. Let's do the necessary algebra. So notice I'm keeping the limit statement because I haven't evaluated at 9 yet, and that's when you lose the limit statement, is when you actually plug in the value for x. So let's do the algebra here. Okay, the whole reason you build the conjugate is because you can see that when you multiply these two together, these two expressions, that your outside and inside terms are going to cancel, and what you end up with is x minus 9. Okay, and now go ahead and look at the denominator when you have to multiply these two together. You could distribute if you wanted to, but you're really losing the effect of being able to cancel this numerator with one of the factors in the bottom in the denominator. So let's just leave it in its factored form and take advantage of it. Let me see if I can clean this up. No. Yeah. I was going to try and clean this up here and move this over here, but it looks like I'm not going to be able to. Okay. I'm going to come down here and I'm going to notice that this is a common factor with the denominator. They divide out into a 1. Let me clean it up one more step. The limit as x approaches 9 of 1 over square root of x plus 3. Okay, now try direct substitution, and what you're going to see is that you do end up with a nice number, and that's going to be 1/6, and that's the same answer we got from the previous method as well. So I guess what we want to take away from this is when you see something of this nature right here and you get indeterminate, you know, think of the factoring technique, which we did, which might be a little uncomfortable because it factors into square roots, or else you might think about, you know, if you see the square root, you might want to think about building a conjugate and then doing the algebra, simplifying and getting the same answer. Okay, let's look at another example. Should have had these typed up. All right, if you evaluate this limit at -3, you can quickly see by inspection that you're going to be divided by 0, and that's never good. I guess what we want to do now is see when you replace -3 in for x, do you also get 0? Because if you do, that tells us that we might want to try the factoring technique to cancel. Now, if you evaluated the numerator at -3 and you did not also get 0, like in the denominator, for example, you may have gotten 7 in the numerator, or -5 in the numerator divided by 0, you're done. That limit does not exist because that would indicate that you have a vertical asymptote. Okay, real quickly, evaluating at -3 gives 9, -3, -6 more is 0, so this suggests that we do need to do some algebra because we get 0 over 0. So keep the limit in the work in your problem. Let's factor the numerator. Now, let's make a wise choice here. Think about this. What's causing us trouble is division by x plus 3 as we approach -3. So wouldn't it be helpful to think that x plus 3 may be a factor of the numerator and we're going to be able to cancel it? So if you're kind of stuck on the factoring, because sometimes students do get stuck there, okay, just try and use the denominator to help guide your factoring. So we know with this numerator, okay, we're going to have x plus 3, x and x, and so let's just test that. If this factor is x plus 3, this one would need to be x minus 2, and it does work if you checked it by FOILing. Okay, so in my work now, I'm going to cancel. As you can see, I'd probably write this in another step and clean this up. Retry the -3. Now you can evaluate. -3 minus 2 gives -5. Okay, and it's okay to jump from here to here and drop the limit statement. You don't want that as part of your answer when you actually evaluated it. Okay, so this is, in fact, your whole answer right here. Okay, all right. We need to stop there because I think we're approaching the end of our time limit.